Should be good. Susan?
Testing. Chuck lost his voice in the planetarium, and I'm losing it now. So anyway, if you'll all find a seat, we'll get started. Now the meeting starts at 7 o'clock, just a little past that. We go through a period of our short business and internal discussions that only lasts about 10 or 15 minutes, and then we'll switch over to the Vice President, who will introduce our speaker. So and this is about as many people as I expect to get in here. If you were here last time, we had so many people, a number of people, including me, were sitting on the floor. So we've tried to manage that in a comfortable way by not advertising our meetings. So we'll see how that works. When we think we're going to get a large crowd, then we'll advertise, and then we'll move to the Fleischmann Auditorium. So we only have a certain number of those cards we can pull with the museum, and so the other ones where we either can't go to Fleischmann or we're told we're not going to, then we won't advertise those. But we're still here. So if you know it, you can come. So we will start with, who are we starting with?
We can go.
Oh, that's right, the merch manager, Pat.
My name is Pat McCartney, and I'm the merch manager, as Jerry was saying. And thank you for the applause before I even speak. I'll make it short, and then you can have more applause. These are some of the items that we have for sale. I'm here at 6 o'clock on meeting nights, so if you're interested in buying something, I do have limited sizes because we're slowly easing our way out of the clothing business, but I will have mugs, tote bags, and caps for the duration. And also, on behalf of the secretary, there's name tags for the club members over there. So please help yourselves and let me know if I put too many T's or S's in your name. And you can reach me at merchmgr@sbau.org. So, back to you.
Thank you, Pat. Diane? You don't have anything? Okay. And let's see, who else? Does anyone, Mike, do you want to say anything?
No, nothing tonight.
Okay, is Tom Whittemore here about the newsletter? Nothing? Okay, good. Well, we'll move right on to Chuck doing the outreach for the coming month.
Okay, busy month. We've already had 2 schools this week, and we lucked out both times. It was cloudy during the day, and we got sucker holes. So we had 167 at one school and 306 last night, so that's my horse. So if you're a registered outreachy, you have to go through a security check here with the museum, but it's quick and dirty. Please come and help out, because there's a bunch more coming, as you'll see. So tonight is our meeting, at First Fridays, and then coming up on Wednesday, the 11th next week, is Cleveland School, their science night. Then on Thursday the 12th at San Ynez Elementary School's STEAM night. And on the 14th, second Saturday of every month, date night on Valentine's Day is the public star party here at the museum. And then on the third Tuesday of the month will be the 17th at Camino Real Marketplace in Goleta, where we set up at 7 o'clock and try to avoid the lights. And normally we'd be looking at the moon, but it's new moon that night, so we will be looking at Saturn while we can, and Jupiter, and some deep sky stuff, because all these people now that have gotten hooked on sea stars can still pull that stuff out of the light pollution. Then on Thursday the 19th, it's Hope School, and Friday the 20th, third Friday of every month, is Public Telescope Night at Westmont College. And then Sunday the 22nd is Museum Free Day all day long. People can come out here and have fun. We're going to have solar scopes set up down by the observatory, and some meteorites on display, and planetarium shows, of course. And then on Wednesday the 25th, it's Mountain View School Science Night. Thursday the 26th is Elwood School Science Night. And then, the month's over. So, there's plenty of propaganda here. If you like paper, we got star maps, moon maps, webpage listings, and bookmarks. And thank you.
Thank you, Chuck. And to Joaquin.
Okay, we can mention about the equipment we have available, Jerry?
We'll get to that in a second.
Okay.
But every time I start to talk to you, I pause because I've got your name confused with Joaquin Rodrigo, who's one of my favorite composers. And you don't look a thing like him. Okay. We also have stuff for sale, as Tom's pointing out.
So we have telescopes anywhere from 8-inch to 11-inch to 5-inch. We've got a couple of beautiful telescopes made by Galmassi that donated to the club. Even one has even an equatorial mount that you can place your Dobsonian telescope on to follow the stars automatically. And then we have eyepieces and some other accessories. So if you're looking for a telescope, probably can get you one for probably half retail on some of these telescopes, good used telescopes. So contact me at equipment manager on the website. I think it's equipment@sbau.org if you're interested in finding a telescope. And this is where you need that nice big telescope, is to look at Jupiter and Saturn up close. There's these new modern little telescopes called the C-Star, S50, S30, and there's a dwarf series 2 and 3. And they have to take wide field views, but they just can't see the moons and the surface features of the planets very well. So you need one of these big telescopes to pull it in. So come see us if you're looking for a telescope. All right, thanks, Jerry.
Thank you, Tom. And this one on the right with Gail Massey.
Oops, sorry.
Those 3 pictures. He just lives down the street from me.
Right.
These are instruments that he designed and built himself. They're unique designs. Very clever. They operate perfectly, and his optics are finished extremely well. So it will be a little different experience if you get one of those, but they will work really well.
Let's see who else is, that's a membership directory.
Yeah,
You got,
directory on
you
sale.
got us guys.
So
How much is
this-
membership? It's $20 a household? That's a lot of money.
I see why you didn't work in marketing. Okay, so we're going to move on to the vice president.
Also, there's some more outreach stuff sort of that I didn't mention, that every Sunday there's solar observing in Palmer Observatory there. Well, it's not on here. Oh,
It's right there.
yeah. No, you had that picture up with somebody looking through the solar scope. Yeah.
Oh,
So,
looking through the solar scope. Sorry.
there you go.
Oh, that's a solar.
So that's in the observatory on Sundays, usually from like 1 to 3, and people bring their hydrogen alpha scopes. The museum had a big hydrogen alpha scope that you see that lady looking through there, but it unbalanced the main scope, and so it's not, and something happened to it, it's not in operation right now. but there's a killer refractor that gives white light views of the sunspots. There's a little hydrogen alpha solar scope on there that's similar. It's similar to Galileo's instrument, and it's got a camera on it, and it shows pretty good views of the sun. And then people in the club bring their Lunt hydrogen alpha scopes, which are really killer, and set them up outside and show views of the sun. And the sun's really active right now, so that's a cool thing to do.
Now, if hydrogen alpha doesn't mean anything to you, the sun is made out of hydrogen. And if anything's happening on the sun, it's going to happen in hydrogen alpha. It's a red light, and the scopes look at just that red light. But you can see prominences and flares if there's any. And on the white light one, you just see sunspots. So it's really dramatic in the hydrogen alpha scopes. And we have a very nice 6-inch diameter one that we sometimes operate out there too. Okay?
Okay with me.
Yeah.
It's way too early to start with the speaker.
We're not doing that. We're not, I thought we got away from advertising the speaker starting at 6:30.
No, the speaker's starting at 7:30, and
Yeah.
that's what the advertising says, so we...
Did we advertise for this meeting?
Yes, absolutely, we advertise for every meeting, actually.
No. At our last business meeting, we agreed not to advertise,
Nope.
not to have the museum.
Yeah.
Okay, everybody, hang on to your seat. There's going to be a disgruntled set of new customers coming in
Yeah.
that are going to wonder why they're so late. See, that leaves us with nothing to do.
Yeah, that's because our business meeting is too quick.
Well, tell us Jerry?
So that's why trying to schedule an event on a time doesn't work.
Hey,
It's
Jerry?
event-driven.
Jerry,
Who's calling right
Jerry,
Yeah.
have people heard about that the Earth is being invaded by llamas from outer space? Yeah, people are calling it the alpaca lips.
Ronnie will be asking you to present on that in December.
Okay.
This is how we empty the auditorium.
I think he's trying to fill in with jokes between the two sessions.
That was the idea. If only I knew a joke.
To tell us your story.
Sorry, Joaquin, we're just gonna sit here and chat.
Yeah.
Our next business meeting is tomorrow, Sunday this week.
That's the Zoom planning meeting.
That's correct.
Move to Sunday.
We will,
I may be able to talk long enough, because I know that's what you do.
Yay.
I got stuff I do with hands and call attention to people, and I try to get people to join. And I do a few things that I like to say plugs the club.
okay,
Fun
well,
club here.
here's your chance. Ad lib it.
Well, I just want to say that we have been very lucky over the years to get some incredible young talent from that giant nebula of education called the Santa Barbara University, UCSB. Last year, we had 3, I think. Joseph Farah, who I believe is here. And Ish Kaul, young man from India, who we've lost track of. He's not here, but do you know Ish? Okay, and do you know Liam Brennan? We had him, I think, in late summer.
Yeah.
In fact, I got him through you. And we've been very lucky because these guys have been riveting. And they're future professors, future JPL scientists, and NASA. And we're getting them on the way up before they merge into a star. Hello, welcome aboard. My God, where have you guys been? We've been waiting for you. We didn't see you.
It's our now.
Spread out. Anyway, here's how I got tonight's speaker, and I'll introduce him in a few minutes. Joaquin Becerra Espinoza was recommended by outgoing and recently retiring UCSB professor Omer Blaes, like B-L-A-E-S, I don't know how it's pronounced, Blaes, because we wanted to get him again, and he's hung it up. But I didn't even have to ask him if he could recommend anybody. He said, get Joaquin. So I think we're going to be rewarded tonight. And I'm finally going to be able to learn what the hell dark matter and gravitational lensing have in common. Because I'm an armchair guy that has heard that dark matter doesn't react to anything. At least it doesn't react to regular matter and light and stuff like that. So we're going to find out the connection. There are galaxies that don't have dark matter. You're going to explain that, aren't you? Anyway, I want to... That's my question, because I always have a question, and we'll have a question. You can probably interrupt him if you want, but if he's on a roll, let him go until the time is right, and then we'll have Q&A after Joaquin's speech. It's entitled Dark Matter Under the Gravitational Lens. And I need to do my show of hands right now, because we'd like to know how many of you are strangers and not members of the club. I was up here as vice president for several years. I've been in office about 7 or 8 years now. The president was elected a year ahead of me, so he's been a year longer. But I used to wonder, I didn't wonder, I just thought everybody was members. And then one night I decided to take a show of hands. How many first-timers, never been here before? Leave your hands up. We want to know who you are. Oh my God. Something I said? Actually, it is. Because we're a fun club. It's a fun science. You know, chemistry's okay, but it can be dull. Just ask a new member that just came up and signed in today and paid his fees, Kyle Luker. Raise your hand, Kyle. He is a member of the Ventura County Association, or no, what's it called? ASBC. Astronomy Society. Lives in Foster Park along 33. Was here in September for Alex Filipenko. 4 of you guys came, and charges twice what we charge to be a member here. Have twice as many members. We need to talk. His job, believe it or not, I was talking to him earlier, is with the chemistry department out at UCSB. We might have you do a talk.
I'm just a machinist and a welder.
I always wondered, I wished I'd taken chemistry, but it scared the P1 out of me. You know, those things that can blow up and heck. In any event, welcome aboard. I want to know quickly, second row of hands, the second bout, if you will, people who have been here before but are not members. We want to know if you're here, if we did something right and got you back. You love us. We're working on you, you know. $20 about what a meal costs at a typical cheap restaurant these days for the whole year. Now the glorious members of SBAU. Mike Hardwick, who's got his grandson from Malaysia visiting here. His name is Michael. Wow. In fact, every male in Mike's family is named Michael. It's amazing in Italian. Almost everybody. Tessa is here with Duff. Tessa, you want to raise your hand? There she is. She's our outgoing secretary, replaced by Mike Lawson. Joe Doyle, I think he's here. He designed our logo.
No, that's...
Wasn't him in the back?
After the alpaca joke, he had to leave.
Something I said. How about Diane Welchenbach, who has a horse over in the valley? Best events coordinator in the world. And if you join the club, she'll let you ride her horse. Arshad Barman, are you here? He did one of our speeches. I'm working on Ian Crawford as one of our in-house members-only speakers. That's a December regular thing we do. And here he is, Sean Kelly, Dr. Kelly, who runs astronomy at City College. I almost read your name a minute ago, but I held off. I couldn't miss it, I'm sorry. Okay, well, don't let that happen again ever, Sean. Big club. Who else is? Dave Grossman, one of the two hit. There he is.
Yay.
The man, Captain Sonification. Read his articles. Trust me, he's all over Astronomy Magazine. 5 different articles. Sooner or later, you're gonna have to sit. There's the other half. He spoke to us. Oh, I got my fantastic poster finally. I left it here that night. He gave everybody a poster. See the goodies you get for joining Santa Barbara Astronomical Unit. Okay, our weekly Monday morning Astro Hour is about to start its 6th year. That's on YouTube, and we're very proud of it. It probably doesn't have as big a following as Neil deGrasse Tyson's Star Talk, but we're working on it, and we really don't care if anybody watches it or not, because President Jerry comes up with the talking points. I somehow host because of my own radio career, and then there were 3 other persons, and we lost Bruce. He died in December, and the other 2 are not here. One's baking bread, retired Westmont College, our newsletter editor, Dr. Tom Whittemore, and then Tim Crawford, who's working on his big speech for December. He's actually granted big permission to let him come up here and talk to us as one of those guys. Okay, we do the podcast, the blog, every Monday, 11 to noon. It's called SBAU Astro Hour. We have a lot of fun.
For you.
And we're about to start our 6th year because we started March 1st, 2021. Just do the math on that. Here's what's coming up. Next 3 months, March 6th. And believe it or not, we're going to talk to museum publicity, not only about the 7:30 to change it to 7, but he's got this lady as being in Fleischman Auditorium, which I don't think we're going to have her there. Dr. Rosalie Lopez, Rosalie, L-O-P-E-S, Lopez, JPL, volcanic expert, will be here in a month, March 6th. Her title, Where the Hot Stuff Is, Volcanoes on Earth and the Solar System. Although Owen in publicity shortened that a little bit. Then the following 2 months, April 3rd, Dr. Matthew Malkin, I talked him into coming from UCLA, a distinguished professor, fun-loving guy that loves Santa Barbara. It's easy to get these guys to come live. You know, if we were Salinas or Bakersfield, it would all be talking about on the street. They come here and make it a working weekend and book a hotel room, and we treat them like God. Dr. Malkin's speech is entitled, What's New with JWST, the James Webb. The astronomy revolution begins now. And then little Dr. Abigail Freeman, F-R-A-E-M-A-N, JPL, Rocky Inner Planets expert, will be talking about us and the other 2 inland toward the sun and the 1 outward, and talking about curiosity on Mars. She's also an expert on that. So let's get to it, because this man's raring to go, and I have a feeling it's going to be a good night. Dark matter, under the gravitational lens, UCSB grad student Joaquin Becerra Espinoza, future PhD, student in physics, studying cosmology under the supervision of Dr. Tejaswi Narella. I couldn't even read my own writing on this. Research will focus on gravitational lensing, it is, and both light and gravitational waves as a tool to study dark matter. Recently, his work has centered on caustic-crossing events and giant arcs. Joaquin is here with his lady friend, and he's also a former writer for the blog Astronomical. Ladies and gentlemen, as we get more guests in, let's hear it for Joaquin Becerra Espinoza.
Your laptop is on? Yeah, okay.
Hello? Yeah, you got that mic. Good. Okay. So, should we start our time? Should we start now? We have 5 minutes.
We should.
Okay, perfect. So, hi everyone. Thank you so much for being here. I'm Joaquin. I'm a student at UCSB. And today I'm going to talk about dark matter and gravitational lensing. So, my objective is twofold today. I want you to first know what dark matter is, what's the deal with that, and also to connect that story to gravitational lensing. And then finally, to understand the rich connection between these two very fascinating topics, right? And how they relate to the history of our universe, cosmology, and structure formation, right? So let's begin by asking, what is dark matter, right? And while that is a very interesting question, I'm gonna back up a little bit and go maybe 100 years ago and change the question to what is the deal with all this missing mass, right? So, 100 years ago, we had a very interesting dilemma. Astronomers were not really sure that the universe was bigger than the Milky Way. So that was a thing, it was a big debate. And I'm not kidding, this was true of the astronomical community 100 years ago. And people like Hubble and Henrietta Levin were really concerned about this. So, prior to this, people thought that nebula or other galaxies were inside the Milky Way. And this changed when Hubble took the first, or one of the first pictures of the M31, which is the Andromeda galaxy, and estimated its size, which is basically 2.5 million light years away, and that is for sure outside the Milky Way. Right? The Milky Way is 100,000 light years in extension, so yeah, it's very far away. So that made the field of extragalactic astronomy very, very interesting and fascinating for researchers to delve into. And in that context, the study of galaxy clusters became really interesting, right? And here what I'm showing is the Coma cluster, a huge cluster with over 1,000 galaxies, I think, and that is 330 million light years away from Earth, so very far away, and has maybe 10 to the 15 solar masses in mass, so it's very, very heavy. Now, of course, in 1930, we didn't know any of this, right? So someone was trying to figure that out, and that someone was Fritz Zwicky. So this very lovely gentleman, this is a real picture of him, he really wanted to know the mass of the Coma cluster. So there's two ways of doing this, well, more than two ways, but we're going to talk about the ways that he used at the time. And one of them is to use the mass to light ratio, which is a very fancy way of just trying to find all the galaxies and kind of put them in a scale, metaphorically, right? You grab one galaxy in the cluster and you weigh it. And then you grab another galaxy and you do the same thing. You take all the galaxies in your picture and try to count the light in your plate. So that was the standard way of doing business back then. To a certain extent, it's still the standard way of doing business. You see the light of your galaxy and then you count how much mass you have. Yet another way, though, is to look at the velocities of the galaxies, right? Because it's a gravitationally bound system. That means that everything's kind of glued together through gravity. This means that by taking the velocity of these galaxies, you should be able to infer what the mass of this whole cluster is, since if energy is conserved, or there's a proportionality between kinetic energy and potential energy, then there should be a way to go back and forth, right? So how do you do this? Because, of course, if we, do a fast forward, even 1,000 times faster, we're not going to see any galaxies move, because our human timescales are just too short for, cosmological changes, and distances are too far away. Therefore, we need to do something slightly different, which is to grab the light from each of these galaxies and split it through a prism. That's called taking the spectra. When you take the spectra of a galaxy, you can basically get a rainbow, just like in the Pink Floyd album, and you can compare kind of all the little slits, or black bands, which are sorting lines, and compare them to what we would see in a laboratory if we were just having atoms emit light, right? And by comparing both what we see in the sky and what we see in the laboratory, we can basically learn the composition of the galaxies or the stars that are there, and also see how fast they're going, because by having this red shift or blue shift, red shift if they're moving away from us, blue shift towards us, we can figure out the speed that they're going. So by doing this and balancing kinetic and potential energy, Suzuki was able to identify basically how much mass there was bounded in the comet cluster. And the result that he got was that the comet cluster was 400 times heavier this way than by counting the light. So, to translate it maybe to a more understandable language, galaxies are going way too fast for the mass that we will be seeing only by light. Right? Therefore, there must be more mass that we're not seeing. And he got this, well, I don't know, excuse my German, Dunkelmaterie. And what he mentioned, or like that's dark matter in English, he didn't really have in mind like a new kind of substance, right? What he had in mind was that there was some cold gas that we couldn't see in this galaxy cluster, and that probably this dark matter was just normal matter, but we couldn't see with the technology at the time. But there was missing mass, right? And I think that that was the key idea that Suzuki brought to the table. Okay, so do we observe something similar in other scales, right? Because a galaxy cluster is very big, and we can, especially in 1930s, this paper came in 1933, we can't claim that we know everything about a galaxy cluster. Is there other observations of dark matter, right? And to answer that question, we need to go back to galaxies. And since forever, galaxies have been interesting for astronomers and their structure and particularly how they spin. You know, because again, we are in, we have very short lifespans compared to, you know, cosmological scales. Therefore, we don't really see our Milky Way rotate that fast. It would be really nice to see how galaxies rotate. And thus, you know, what we can try to do is to use Newton's laws, like gravity. And if we follow gravity, what happens is, as we are following away from the center, and we include more and more mass distribution, our star is going to start spinning faster and faster and faster as we include more and more mass. Okay? However, when we reach the edge of the galaxy, then we're not going to include any more mass, since all the visible matter is completely exhausted. And therefore, the star is going to be able to decrease in speed as we go farther and farther away. Right? At least that's the intuition if we only follow visible matter. And to be perfectly clear, there's precedent for this. Right? This is the solar system. So in this plot, what we're plotting is orbital velocity over radius. The radius is in astronomical units, so for one astronomical unit. Yeah, it's an astronomical unit. The distance from here to the sun. So, because the sun is so massive, right? It's 99.9% of the mass of the solar system. So, if you are going outside of the sun, you're going to start dropping in speed very quickly, and that's what we see. Right? So we expect the same to happen for galaxies. As you get out of the galaxy, the speed should start dropping. And Rubin, in 1970, had the same question, like, well, how are galaxies spinning? And she was looking at M31, which is the Andromeda galaxy. And she was looking at the speed of the stars in the core, in the bulge, and in the disk, right? And in the outskirts, turns out that the cold gas that Suzuki was complaining that maybe that's dark matter. It actually does emit radiation, the 21 centimeter radiation. And that was discovered around the 1950s, so now Vera Rubin had that information, and she could use that, that emission of light to look at how fast gas was rotating outside of the Milky Way, right? So, she obtained the velocities by looking at these emission lines, and she discovered that things were very flat, actually, right? So if you compare that plot of over here, that's orbital velocity, just like before, and then this is the distance from the center of the Andromeda galaxy. The unit is minutes of arc, so if you extend your pinky to the sky, that's a degree. And if you divide that by 60, that's 1 arc minute, right? So that's what we're seeing over here. And in this picture, 30 arc minutes corresponds to this distance. Okay? So as you go away from the edge of the galaxy, you can see that the velocity still is very flat. Right? That is not the expectation that we had from the solar system. So that is definitely something weird. Right? And Vera Rubin said, like, well, that's definitely dark matter, right? Because it's something that is interacting gravitationally. It's giving more gravity to the galaxy, but we can't see it, right? And this diagram that I'm showing over here, that's like what we believe dark matter looks like. I mean, not really in terms of visually, but that is a spherical distribution around a galaxy, right? And the galaxy is like just in the middle. That way, when you're going away from the edge, you're gonna see that the velocity is gonna keep constant till it drops off. Okay? So, it turns out that since then we've done a lot more research, and we figured out that most of the matter in our universe is dark matter. So it's around 84% of the whole thing is dark matter, which is crazy. And stars are actually 1.5% of the matter of the universe. Can you believe that? 1.5. And then the rest is a kind of diffuse gas. And we know this percentage is very precisely because of something called the CMB, but today we don't have time to talk about the CMB. So we're not going to go into that kind of worms. Maybe another time. It's really fascinating. It's beautiful. So I want to be very clear here. There are many ideas about what dark matter might consist of, like theories, right? What is dark matter? And for people in the audience, maybe they go to a particle physics talk and talk about like the WIMPs or like fuzzy dark matter, things like that. Or maybe a dark sector or very exciting new physics. And this all might be true. Some version of this might be the truth. However, that is not what we're doing here, because dark matter is first and foremost not a theory, it's an observation. It's an observation of missing mass, right? That's why I claim so confidently that dark matter is real, because we see it in observations, right? We see it in observations of galaxy clusters, and we see it in observations of rotation curves, we see it in the CMB, and so on and so forth. So, that's the first lesson. And we're going to change gears a little bit to talk about lensing. So what is a lens? A lens, I would say, is any kind of object or substance that bends light. I think that's a very simple definition. We're very used to dealing with lenses all the time. I mean, I can't live without my glasses. So I think that it's very intuitive how lenses work. The question is, can we get a lens in space, right? And the answer goes again back to 100 years ago, and when Einstein in 1915 came out with general relativity. One of the first things that he was thinking about was, well, how can we test that my theory is correct, right? And a lot of astronomers were preoccupied on how we can, show ideas about space-time. So, what is general relativity? It's this idea that gravity is not really a force, it's actually the curvature of space-time, like you can see in this diagram. So instead of bodies exerting forces on each other, they're just bending this surface that we call space-time. And if we can bend space-time, and light travels in, kind of straight paths, then as space-time is curved, light from this perspective is going to keep going straight. But now that there's curvature, it's going to bend, right? And from that perspective of the light, I'm still going in a straight line, but from the outside, you can see like, oh, there's something crooked over here, right? So Arthur Eddington was very excited about this. So like, well, maybe I can help you out, try to prove a prediction of general relativity. So this was the main idea. So at night, you can go out in the sky and picture maybe a couple stars, right? And during the day, of course, you have the sun. You can't see anything. And it's very, very bright. But if you get an eclipse, right, what will happen? And in the same patch of the sky, if you get an eclipse, you're blocking the light from the sun, but the sun is still there. So, that means that we can use this as a way to test if the sun is bending space-time. Why? Because if the sun is bending space-time, the starlight from those stars is going to get bent. And if we take a picture of the scenario without a sun and the scenario with the eclipse, then we can take the difference between those two images and see how the shift occurs, right? And that's the point, or like the main idea that Eddington had, and it's known in history as the Eddington experiment, right? So in 1919, actually even a little bit before, 1917, they started planning this expedition, right? So this is war times, and this is like really fun because, you know, Einstein was a German, and Eddington was a British guy, right? So this was, you know, kind of a controversial thing at the moment. However, Eddington started his expedition and planned to go to 2 different places. So they knew that there will be an eclipse going through Brazil and in Africa, right? So in Brazil, I think it's called Sobral. Sobral in Brazil, and then in West Africa, it's El Príncipe, right? So there were 2 expeditions, and then they needed to go with a lot of equipment actually to mount a telescope, and then mount photographic plates to take the picture of the eclipse. So they went in ship, and then when Eddington arrived at El Príncipe and had everything set up, it was cloudy in El Príncipe, so he couldn't get a picture. However, the people in Sobral in Brazil, they were able to take a picture, and this one I'm showing over here. And now this eclipse was particularly perfect because it was in front of the Hyades star cluster, just a lot of stars, right? Just like I showed in the doodle before. Therefore, they had a lot of data to prove if there was any deflection at all. Right? And I'm showing here data from Eddington's paper. And as you can see, again, the units over here are rate of displacement in arc seconds. So I told you that if you put your finger out, that's a degree. Then you divide that by 60, that's an arc minute. You divide that by 60 again, and you get 1 arc second. Right? So it's like very, very tiny. And the observations show that the Newtonian prediction, which was our understanding of gravity before, right, is nowhere near the data, right? And Einstein's prediction, which is the curve over there, explains better the fit, right? I mean, it's not perfect because it was in 1919. Since then, we've done other tests, and we discovered that this relationship holds actually very well. So, oh, sorry, how can I forget? This is my favorite maybe headline from the New York Times ever, because it says, stars not where they seem or were calculated to be, but nobody need worry. I think that's amazing. Anyhow, we can kind of zoom out a little bit and start to study lensing as a physical phenomenon. So we're always, in every lensing situation, we're going to have a source plane, an image plane or lens plane, and then us in Earth, right? So in the example before, we're talking about just stars in the Hyades clusters. That would be the source plane. The image plane would be where the sun was, right? And then we would see whatever is projected in the image plane. Okay, so there's 2 types roughly of lensing. One of them is called strong lensing, and it's very self-explanatory. It's a very strong bending of light. And strong lensing can have various effects. One of them is that we can see double, actually. So if we have a light ray coming from the source, it's going to get bent by that lens. And if we have maybe another set of rays, it's also going to get bent, and we're going to see 2 images. So this view is from kind of perpendicular to the whole situation. But if we see it face on, we're going to be, seeing, that over there, which would be like 2 images of the source, right? And that happens because we're projecting, again, like light travels in straight lines, so we're projecting that image in the lens plane back to the source. So that's why we see 2 little stars. And now this should be familiar to all of you because if you've been in an aquarium ever and you're like looking at the edge of the tank, you maybe are seeing double, right? Like you're seeing like some fish. And it's again the same phenomena where you're basically being, the lens is the edge of the tank and then you're seeing two little fish. Okay. Something like this also happens in cosmology, very big scales, right? So in 1979, we saw the first twin quasar, and I'm not going to try to pronounce the lens because that's that galaxy over there. So we see over there, yeah, that kind of yellow dot over there. And the twin quasar are the two big stars that are basically identical, right? A quasar is like a very active galactic nuclei from very distant galaxies. And this quasar is 14 billion light years away, so it's very, very far away. And it's being strongly lensed. One of the effects of being strongly lensed is that you get super magnified as well, so you can go to very, very high distance, long distances and still see a source, right? Just like with a magnifying glass. Okay, and how do we know that these things are kind of the same? Is because, well, people at the time were like, no, there's no way, right? And they said like, well, they're very similar, but maybe they're just like physical twins, right? Like, we don't know if they're the same object. And it took basically taking their spectra, which again is grabbing the light and splitting it in a prism, to see that they're exactly the same object, right? As you can see, the curves are identical. Okay, so, oops, there we go. So the other kind of lensing is something called weak lensing, which is a little bit more subtle. It's like a tiny distortion. And it's actually really hard to pick it up with only one source. And the best way that I have to describe it is that like everything gets a little bit tilted. And the way to detect this out in the wild is to actually take many, many sources and find a correlation between them. So let's do a little exercise. So over here is a cluster, right? And then it's really nice to do this picture. And if you see over here,
Joaquin, you got the red laser somewhere?
oh yeah, I do have a laser. Thank you. That's amazing. Yes. Thank you so much. So over here, you're going to see that we have a lot of galaxies. Not a lot of galaxies. And we have some strong lenses, like over here, this is a very elongated galaxy. However, we have a lot of what we would call normal galaxies, just dancing around here, very concentrated. And you would think that maybe those are not strongly lensed, or like they're not lensed at all. But if we have a knowledge that there's a strong lens over here and over here, maybe they are being affected by the same gravitational potential, it's just that they're not being super affected, right? And again, a very kind of big problem of lensing is that as opposed to, you know, the eclipse where we have an access to the source plane, we have a way of knowing how the sky looks like without the lens, right? In cosmology or like very big observations, we don't have access to how things really look like. We only have access to the image plane. We only have access to how things look after being lensed. And if you really think about it, most of the universe is lensed, right? So most of the things that we're looking at have been filtered through a lot of bending of space-time. Which is kind of creepy to think about. It's like Plato's cave. Anyhow, this cluster is very special. It's called the bullet cluster. It's yet another evidence for dark matter. Right? If we look at how its composition is, with this data I was taken with the Chandra telescope, we can see that in the middle we have a lot of hot gas, right? And this cluster is called the bullet cluster because it's actually two clusters that collided with each other a long time ago, right? And when two clusters collide, the gas literally shot through each other, right? And we see a bow shock over here, kind of showing that this, like a cluster went through the other cluster, and all the gases in the middle, right? However, most of the galaxies over here are not in the middle, and they don't have anything to do with the gas. So how is that happening, right? the answer is that dark matter is holding these galaxies together. And we know that dark matter is here because of weak lensing. Right? We know that all these galaxies are systematically being lensed, which is really fun. Okay. So, hopefully now, the link between dark matter and gravitational lensing is clear. Dark matter lenses most of the light in the universe, and I think that was really cool. So, now we're in a great position to talk about scales in the universe. Now, we know how dark matter acts in a galactic scale and in galaxy clusters. If we go up in the ladder, right, we have the large scale structure of the universe. And this distribution of galaxies, every point here is kind of like a galaxy. It is very regimented by dark matter, right? Like our understanding of the universe is very much dictated by what we learn over in these scales. If we go down the mass scale, then we're going to see dwarf galaxies, which are kind of the limit on where we can have like gravitationally bound objects that host luminous matter, right? So if we go even smaller, we can see completely dark subhalos. Now, this is where it gets tricky, because we have luminous counterparts for every part of the ladder, except for completely dark subhalos, right? So the mass of a galaxy is like 10 to the 12 solar masses, very heavy, right? The mass of a dwarf galaxy is 10 to the 9 solar masses. When we're talking about dark subhalos, we're talking about 1 million solar masses, which is still heavy, but it's not really heavy enough to have more gas or like stars to hang around there and tell us like, hey, we exist.
Well,
right?
Joaquin, can you tell me again what the 10 to the 9th and 10 to the 12th, what's that in billions and trillions is?
Oh, so 10 to the 6 is a million, and 10 to the 9 is
billion.
1,000 million.
Billions.
That is...
Okay, billions, and then...
Yeah, and 10 to the 12...
Be trillion.
Yeah.
Okay.
Yeah. So, yeah, a lot of math. Okay. So, now here's where things get interesting, right? Because we know our theories of structure formation tells us that all of this starts with these guys, like the really tiny subhalos that start merging with each other and make bigger and bigger and bigger halos, right? And that's called hierarchical structure formation. And as we can see from, for example, this plot, which we'll talk about like the mass of these subhalos, and this is their abundance, right? Dwarf galaxies are sitting right over here, and for every power of 10 in mass, right, we're going to be talking about a factor of 10 in abundance. So there's, if we have 10 powers, so for instance, dwarf galaxies, which are 10 to the 9 solar masses, right, to completely dark subhalos, we have 1,000 more dark subhalos than dwarf galaxies, right? That's how it goes. It's like a power law. Okay.
Sorry, what do you mean by a halo?
A halo is, it's like a sphere of dark matter. So when I showed, for example, like the galaxy that was immersed in a huge dark matter halo, that was required to explain the rotation curves, right? So a halo is like a big sphere of dark matter, and the galaxy is like at the bottom or at the center of this halo. So what I'm claiming here is that all of these big halos form by kind of merging like Pac-Mans to each other. Right? They just like eat each other, and then with a lot of time, they form these big things that like are galaxy clusters and stuff like that. Okay, so this is a simulation of a galaxy, right? This is like putting our X-ray vision and being able to see what we are not supposed to see, right? So these are completely dark subhalos that are surrounding these galaxies. Like I mentioned before, even though dark matter is an observation, we still have theories of dark matter. We're trying to figure out how does dark matter look like in these very small scales, right, below the dwarf galaxy scale. And there's two like competing theories. One is called cold dark matter, and the other one's called warm dark matter, that predict different amounts of subhalos surrounding these galaxies. Now, both of these theories still need to replicate what was happening here, right? They still need to explain all of the structure that we see over here. So this story doesn't really change. We know that this is it is predicted by kind of this mass function. However, for what's below dwarf galaxies, we need to figure it out, and that's kind of the problem that a lot of scientists are working. And what I want to claim here is that gravitational lensing can open the doors to learn about these very tiny, tiny subhalos, and they're invisible, because we can see their effects gravitationally. We can't see them, host any luminous matter, but we can see their effect on luminous matter that is far away, right? So back to lensing, I'm going to talk about something that probably all of you are familiar with, which is if you're swimming in an absolute pool, you're going to see this kind of lines that are formed in the bottom, like in the ocean if you're scuba diving, and those are called caustics, right? And a caustic comes from the Greek that, well, means burnt, right? And it's when all the light gets concentrated in a single point. So for instance, like in the example of the water, we can see that a tiny bulge of water can focus all the light into a single point. So if you have a lot of ripples in the water, you're going to get all these curves that have a lot of light, right? So just like when you're not supposed to be burning ants, but if you ever did that, you're doing it. Yeah, so it also happens for you guys that are married, if you have a wedding ring and you put it at a right angle, you're going to be able to see this caustic curve over here. It's very beautiful, or like in any curved surface, in a cup as well. Yeah. So, again, the question is, this daily phenomenon that we see everywhere, can it happen in space? And the answer is, well, yes, right? So this guy over here, Joaquin Becerra Espinoza, really wanted to see if we could see very far away stars. So normally we can't see individual stars that are very far away. We need to use with galaxies. And when I say far away, I'm talking about cosmological distances, like galaxies very, very far away when they're like the early universe. And if we try to follow this dot over here, the blue dot, as it's crossing this gravitational potential. And again, I want you to focus on this diamond over here that looks like the caustic in the cup. You're going to be seeing that it's getting a lot, that source is getting lensed and producing multiple images that are the white dots over here. Okay? So we can delve more a little bit into it. So if we pay attention into this square over here, and we zoom in, what we're going to see is that as this source is incoming into this fold, it's going to create two images that are kind of symmetric around a point, right? And that's what you're going to be seeing over here. Two things that are merging together. So this is called a fold, and I can't resist this analogy. Maybe I'm going to put this down a little bit. Because it's when you have like a sheet of paper, and you try to fold it, right? Fold the sheet of paper, and you start putting holes on it, right? If you put holes into this sheet of paper, you're going to have two images, or two holes. And you can keep doing that until the edge of the paper, and then you're going to get when the two images merge. And then after that, when you try to hit an empty space, you're not going to get any images, right? And that's why this is called a fold. You're literally folding space-time, and that's how your lens is creating these images. Okay, back to the microphone. So, what are the effects of dark matter into this configuration, right? So now that we know how a fold works. So if we have all of this, if we start at the beginning of these arrows, right? If these are all kind of tiny stars. What would happen if I add a dark perturber that doesn't emit any light, right? Like a dark matter subhalo? Well, things would be shifting a little bit, right? Because of its gravitational effect. Just like we saw in the eclipse when we had a lens, things shifted a little bit. we will see an effect similar to this. And if we have a smooth lens, right, for instance over here, we would have this critical curve, and the stars that we're going to see are highly magnified. And if we have many of those sources, we will see that the critical curve is roughly very straight. Again, we're zooming in into the proximity of this fold. And if we had a lot of invisible dark matter over here, we would see that this symmetric arrangement would be a little bit disturbed, right? Because all the stars would shift a little bit in unpredictable ways. And therefore, this critical curve, I'm exaggerating here, would be very wiggly, and the stars would be very far away from where they would be otherwise, right? So let's try to put an example onto this. So this cluster is a lovely cluster, it's the SBAU 370, and I want you to focus over here. This galaxy that looks a little bit like a Salvador Dali clock, like very kind of bent. If we zoom in over here, we can see that it is very strongly lensed, right? Like this is it's being very stretched, and JWST was able to take an image of this galaxy and see over here all of these little dots that I'm gonna zoom in again. All of these circles are individual stars that are crossing through this to the galaxy over here. So in this galaxy, there are a lot of stars, and because they're close to this critical curve, we can see some individual stars over here. For instance, like in B, we can see these stars are counter images of each other, or over here, right? So this is amazing because the galaxy that is being lensed, so the source, that galaxy formed when the universe was roughly half its age. So we're seeing an individual star that is, emitting light from when the universe was half its size. Okay, so that is really cool. But we have more, even more clusters. So this is the channel we call MAC S0416 cluster. And we can see here, if we zoom in, a really curious arc called the wormhole arc. Wormhole you would know, for its contribution to art, right? And if we pay attention to the wormhole arc, we can see that it's a very symmetric kind of configuration. Again, it's a galaxy that is being strongly lensed, very elongated. We can see signatures here on number 1 over here, which are kind of images of each other, and W1, 2. And again, the smooth lens, if we model the whole mass distribution of this cluster, we will see that the critical curve, which is where we're getting most of the magnification, is slightly off from the kind of axis of symmetry that is very visible in this cluster, right? So if we take kind of the middle point of this critical curve is a little bit off, and that is very interesting. That's a hint that our modeling is not correct. Right? We need to account for more dark matter that is not there, and that's what myself and some collaborators have been looking at, that if we look at all the observations from this, I'm not going to call them stars, these are going to be called knobs, because for this we haven't confirmed that they're actually stars. They can be star clusters, or like slightly bigger configurations or groups of stars. They're, again, being multiply imaged, so we're seeing double, right? And if we look at the lens model for this galaxy, so we trace all this mass and we try to find the critical curve, we see that the reconstructed images, with predicted images, where they should be, they're a little bit shifted from where we actually see them. That means that there must be a fraction of the dark matter that is not smooth, it's not like in this big cluster, but it's in fact resides in small substructure, small dark matter subhalos. So we thought with some collaborators that this was really, really cool. And the actual result, we found that 0.3% of the mass hosted in this galaxy cluster comes from these subhalos, right? So a very small fraction, but again, because there's so many of them, they have a gravitational effect. And this story is consistent with our current theories of dark matter. So I think that if we find less shift from what we see here, we can maybe in the future start comparing different theories of dark matter that can tell us if there's a lot of this substructure or there's not a lot of it. So that's it for me today. Thank you so much.
Q&A, everybody. Who has those questions? President first.
The dark matter, is that considered to be stable over time? Or is it like, if it's a particle, is it its own antiparticle and does the stuff eventually combine and disappear?
So we're talking about dark matter theories, right? So there's many of them. The championing one right now, like the standard picture that we have, is called cold dark matter. And that's, by the way, we can here. It predicts kind of this map of substructure, okay? So there's many particle physics theories that can lead to cold dark matter, right? Many. Some of them have that property that I just said, that like it's a particle and that it can be its own antiparticle. Sorry, you want to ask?
But do you, on a macroscopic level, whether it's particles or other, do you think that you will be able to detect or have seen any trend in the population of dark matter?
So, yeah, if it's, I see. So, if it's its own antiparticle, they will annihilate, right, and emit light. And we will be able to see that light, hopefully, right? And we haven't been able to see that, or like find that light. So right now, that's not a favored candidate. There's other theories like self-interacting dark matter that tell a similar story, but that don't require necessarily that it annihilates to light, and that can be a possible explanation, because again, all the theories of dark matter need to work in all this galaxy scales, cluster scales, large structure. So that story is the same. So it will only change in the small scales, right? And the abundance of dark matter, once you know basically what theory you're using, wouldn't change. So if we know that dark matter is cold, this would be the abundance, right? It would depend on like local environment stuff, but it wouldn't change that much. Now, if it annihilates, maybe certain peculiarities of the environment, of the cross-section of the particle can come into effect. And yeah, that's how it changes. For sure. Yes.
Okay, we exist in a spiral galaxy.
Yeah.
Is the Earth part of dark matter, and is that true?
Yeah. So that's a really interesting question.
If you can't see dark matter, how do you know it exists?
Yeah, exactly. So we know that it exists because of all the observations of, I admit, they're indirect observations. However, they're still astrophysical observations, they're real, right? And, sorry, I wanted to go over here. Let's go to the, so this is an observation of dark matter, right? However, if you're asking for how, well, if we are in this kind of ball of dark matter, how much dark matter is here, right, this room, right? I think that in the solar system, if we went to the orbit of Neptune and collected all the dark matter inside the orbit of Neptune and put it into an object, it would be about the size of an asteroid. So it's not that much, right? Again, it's very diffuse. I think that if it's probably like 10 times bigger than the disk itself, more or less.
So there don't need a physics works for Neptune.
What?
Newtonian physics works for Neptune.
Yeah, I mean, like, Newtonian physics works phenomenally well in the solar system. I mean, like, of course, Mercury has its effects on GR, but the effects of dark matter are not very appreciable in the solar system. And you know who would know this really well are particle physicists that are trying to find dark matter desperately, and so far coming empty-handed, because if we understand dark matter how we do in cosmology, is something that we call number density, or like how much dark matter there is per unit volume, would be very tiny in everywhere, right? Like, and particularly in the solar system, because it's tiny compared to a galaxy.
So why did he say Neptune? You want to explain that?
This says you take all the dark matter inside of Neptune.
Yeah,
Neptune's orbit.
that's there.
You know, it would add up to the same gravitational tug as a single small asteroid would have. It's not the gas giant that's on its side, but that's yours. No, that's what I think we're talking about.
So basically, the distribution of dark matter is not homogeneous. It can be in clumps.
Yes, it is very clumpy. And actually the clumpiness, okay, so you're gonna make me think about the CMB. I should have talked about the CMB. So the fact that dark matter is clumpy is actually very important. It tells us where all the galaxies are and why they're there, right? So dark matter, as we believe in the early universe, we were a very hot soup of stuff, right? Undifferentiated, with everything like kind of at one. And as that soup started to cool down, dark matter was one of the first things, because it only interacts gravitationally, to like decouple, or like just left the soup. And it started tugging with gravity, you know, at the rest of the soup. And at some points, when luminous matter, you know, disentangle or decouple from this soup, that luminous matter started following where dark matter was before. So maybe you've heard this before, like dark matter is kind of the seeds where all the galaxies and galaxy clusters formed, because they had a lot of time to kind of collapse into a little bubble, but then you know, all the rest of luminous matter followed, and that created the galaxy clusters and galaxies that we see today.
Could you say something more about that final bit that was like super mind-blowing about the roughness of the dark matter?
The roughness.
You said that you had these little deviations.
Yes.
Right, which showed.
Sorry. I'll go to the end.
Sorry.
No, don't worry.
Yeah. You had these lines. Yeah, we're getting close.
Yeah.
You had these lines, and you said that there were these deviations.
This.
One.
Okay.
You said that there was something about the dark matter having some structure to it. Is that what I understood?
Yeah. So.
Could you explain that a little more?
Over here, so remember that a critical curve is like kind of the lens plane version of a caustic, right? And close to it, you're gonna start seeing double, right? Like the stars that are back there, or like the clumps, are gonna be kind of mirror of each other, right? That's always the case. If you have a lot of invisible dark matter, right, that is disturbing, you can think about it like a lot of like a rain, like a lot of droplets here, and disturbing this whole image. Then that's going to shift, just like here, right? These perturbers, these invisible perturbers, are going to shift ever so slightly each image, right, in an independent way. That's going to break the symmetry from this critical curve, and therefore the fact that our models predict one critical curve and then the images are kind of a little bit off that tells us that there's a lot of these dark perturbers over here, right? And how many of these are around the critical curve will basically tell us how far off we are from the line, this line over here, right? So if this is the critical curve of this arc, right? And this is the reconstructed images, the diamonds, right? And the observed images are the squares, which are like basically these ones over here. You can see that they're a little bit off, right? The model is not fitting the observations.
What are the purple lines?
The purple lines, they're called surface density lines. They're not super important for this discussion. It's telling us how much mass there is.
So,
Right?
so is this showing that there's some anomalies in the distribution of the dark matter?
Yeah, it's showing that there's, yes, it's showing that in very small scales, dark matter is very clumpy. And that therefore we have these dark perturbers that we can't see.
Okay.
And they're disturbing the image.
Okay, and
Yeah.
the fact that it's clumpy, that sounds really important. So why exactly is that really important?
So it is very important because, what?
It's an observation here.
I mean, yes,
Characteristic.
but
We're sort of getting a dark matter.
yeah, so it means that we can differentiate between these two scenarios, right? So if it's very clumpy and has a lot of abundance at these small scales, we're gonna see a lot of these perturbers, and therefore we're gonna see a lot of deviation, right, from the kind of perfect story. If we have a more moderate amount of dark matter, if it's more sparse and it's clumpy but like not as abundant, then we're gonna see less deflection of the images, and therefore we'll have a different reconstruction.
So it favors the cold dark matter? Is that
For now, it does, yeah. I mean, this is still work, I mean, this is published, but like it's a preliminary study and we need to look at more and more galaxy clusters. Right? I think you...
Well, can we assume then that we're sort of getting a dark matter by observation without actually seeing it? We're trying to discern what it has and what it does. Can we assume that dark matter has gravity and can bend space-time because of its characteristic?
Yes. I think that's like the only property of dark matter that we're very sure of, that is gravitational and that it interacts with the rest of, quote-unquote normal matter only by gravity.
But bending space-time is a definition of gravity, right?
Yes. Yeah.
And so, by definition, dark matter has gravity, or we assume that it does, because it can bend space-time as well. And do we have any proof of that, any observational proof of that?
I mean, yes, I
I mean,
think that...
without getting into it.
Yeah, but like I think that maybe like this cluster, the bullet cluster is one of the most kind of striking evidences of this, because this whole bullet cluster could only be explained if we invoke dark matter, right? So think of this, like if we have two galaxy clusters that are full of gas and galaxies, right, and dark matter, right? Let's think component by component. The dark matter only interacts gravitationally, right, and with nothing else. So it would go through no problem, right? Which are the blobs that you're seeing over here. The galaxies, they're also very, and the stars, right? They're also basically, we call it collisionless, right? Because let's see. The sun and Proxima Centauri, right? The sun, if we shrink both of them, so Proxima Centauri, of course, is like the closest star that we have to Earth. And if we shrink them to the size of a ping pong ball, right? They would be 800 miles apart from each other, right? So now, then from Santa Barbara, that would be going to like Phoenix, right? So now if I ask you, can you aim a ping pong ball and throw it to Phoenix from here and expect them to collide? Not really, right? Therefore, all of this, I mean, like technically if you do a very precise experiment maybe, but like not in actuality, right? So like these galaxies and stars are just gonna go through each other, they're not gonna collide because space is so big, right? The gas that is here in the middle did collide, right? Those are like basically clouds of gas, and they shot through each other. So that's why we see this pink over here. And most of the galaxies and stars that we see are in these big blobs, which are being gravitationally lensed, right? Therefore, the only way that we can, interpret this image, which is an observation, right, is that dark matter is bending all of these galaxies that are in the background. Yes.
Is there a correlation between the map of CMB and distribution of dark matter?
Absolutely, yes. I think that there's a one-to-one. Yeah. Again, the objective of this talk was not to talk about the CMB, but I think that next time that I do a talk like this, I will talk about the CMB because it's coming up more than I thought it would be.
Okay, so going back to something you said about the clunkiness of dark matter, you said matter, like galaxies and mass and space dust and all that follows dark matter in the early universe. So how does that relate to like the cosmic voids and the expansion of the universe? Does that mean like dark matter is flowing out of the cosmic voids and then all the galaxies are following it and clumping together? And
That's a great question.
Galactic filament we see?
Again, a CMB question. Okay,
So do voids have a lot less dark matter than?
Yeah, so in the early universe, and this soup, very hot soup, you have overdensities and underdensities. So overdensities is what we're most used to talk about because overdensities are where dark matter collapsed and then it formed galaxies and galaxy clusters and so forth, right? But the underdensities is where there's less dark matter than usual. And those, we believe, are the underdensities are where there's nothing, there's empty space, right? So that's the voids.
Grew into the voids.
Yeah. I mean, that's, yeah.
So then like the structure of the universe is taking, it's just like following the lead of dark matter, basically?
Yeah. I mean, the structure, exactly, yes. And that's why this picture over here,
the cosmic web.
the cosmic web is showing us.
Oh, that's interesting. So at that scale, the largest scale is dark matter just like completely overpowers gravity or mass?
Yeah, I mean,
basically?
yeah, because again, 84% of matter is dark matter, so yeah.
And it has its own gravity.
Yes, and again, yes, it has.
But the larger the scale, the stronger dark matter is, and the smaller the scale, the weaker it is. Like the solar system level, it's like
you can think about it that way, yeah, because as you go like bigger and bigger, like baryons stop being. Oh, sorry, I said a technical word. Luminous matter is not able to form bigger than that. Like galaxies and galaxy clusters are the biggest that we have in terms of what we can call a structure of luminous matter, right? And then the rest are just connected by this filament of dark matter. And so
What was the technical word?
baryons.
Baryons.
Yeah, which is astronomer for luminous matter, normal matter, the one that we interact with every day. Yes. Yes.
What causes the heating and the cooling of the different gases? Is that just in relation to the size of the galaxies they surround? And like when the cold punched through the hot galaxy, was there any transfer in that?
I see. So for the bullet cluster, so you're asking about the bullet cluster?
Yeah, and just like what's causing the heating and the cooling of that
So
gas?
when the two gases collided, right, they, as a result of the collision, I can have the number over here, they got really hot, right? I mean, gases are in general, like in the context of galaxy clusters, gravity is heating up the gases, which is a very fun like fact. It's called, again, the technical word over here, gravitothermal collapse, right? Take the word for you. Which is, again, it has to do with this argument that Swiki was talking about, where he said like, oh, we can equilibrate kinetic energy with potential energy. That's called the theory of theorem. But to just go back to your question, when these two clusters were colliding, as they collided, the gases that were already hot, as they collided, they became hotter. Right? And then they started, the hot gas emits X-rays. And that's why we're seeing them here with the Chandra Space Telescope.
Gotcha.
Yeah.
Okay.
Yeah.
What if our city college professor?
I got a question, yeah.
Yes.
Can I ask you- Yeah, so it's, you showed us one example of this filament, it's beautiful, all of the little stars and everything. How do you pick which filament you're gonna study? There's so many of them,
I mean, by filaments, you mean like the large scale structure or like the
Yeah,
arcs?
when you started to look at the analysis clearly of
Oh.
the displacement and to be able to see the clumpiness of the dark matter.
Yeah.
What is your next project? What's your
I
next
mean,
paper
my
gonna
next
be about?
paper is on this guy over here, which I'm not showing results because it's not finished yet. The other one I'm showing because we're very busy up and it's from literature. But this one, Hour 370 is my favorite. I mean, like this guy is called the Dragon's Tail. Yeah, and it's just phenomenal. Okay, so how do we choose arcs? So one of them, of course, is convenience. Some really nice astronomer did an observation of this really nice cluster and saw all of these stars, and the data is just there. Right? Like you just go and like use it. You don't need to apply for more time to look at a different cluster. Like the data is there, so it's nicer. If I had a limited telescope access and I could do all these observations, I would point it to something called the Hubble Frontier Fields, which are like the Hubble Space Telescope, like maybe 10 years ago, started doing like lensing maps of all of these galaxy clusters that have very strong lenses. Something that now Euclid is going to do, is pointing to very far away and trying to find these maps. And with that, we're starting to find a lot of these clusters that have these elongated arcs. And when you have an elongated arc like this galaxy, it's like super bent, then you can, and if your lens map tells you that a critical curve is going through it, like here, which is, if it's that elongated, chances are that you are kind of hitting it over there, then you can try to apply for this observation. And now that you mentioned it, let me talk to you a little bit about how this picture was created. It's actually a difference picture, just like the eclipse picture that I showed you before. And that like 1 year, in 2022, it took an image of this galaxy, and then another year they did another picture, and then they subtracted. And that's how what we're seeing here, 2022 and 2023. And we're seeing how these stars basically pop out in and out of existence in our field, right? And we can see them. What?
The lensing is shifting.
Well, in a year, again, because we're feeble humans, nothing, like the shift wouldn't really be appreciable, like in time, like it's basically fixed. The only reason that sometimes the stars disappear and appear back is because of something called microlensing. And I don't really want to get into that, but basically there's a lot of stars in the cluster itself that are obfuscating the view, right? They act like a little extra deflector, and then they say like, oh no, this star is not going to appear now, but then it will appear later. So, and that is, its variability is much more closer to human, like a year is like very nice for a human to be able to pick up. Yeah.
When I first heard about gravitational lensing, I started looking up and thinking, why isn't the sky just one big hollow mirror? Gravity's pretty strong, and you know, when the Webb finds those 5 globs that they claim were early galaxies, how in the world did the light make it from there to us, 13.5 billion years without ever being affected by the zillions of galaxies that once they went by? It wouldn't take much of an early influence to really make it miss us, or be why is it not like that? You know what a hollow mirror is? You ever been in, you know, we've all been in those.
I think that, unfortunately for you,
why isn't it like that?
I think that it a little bit is. Like, so the older life in our universe is the CMB, again, the CMB. And that light is being lensed.
Really?
Yes. Yeah. It's being lensed a little bit. It's like the weak lensing. It's not being strongly lensed, but it is enough that it has an effect, and we need to take care of that. And actually, again, dark matter plays a huge role on that lensing, of course. And it is thanks to that lens that also we know very precisely why the CMB, so why we have a certain percentage of the mass of the universe is dark matter, right?
Okay, well, I was out to give you your goodies, but before we go, just a couple quick questions. Joseph Farrar, did you have anything you wanted to add or ask? Your friend who talked to us, what was your speech about? You talked to us twice, right?
I did black hole stuff.
Okay.
Joaquin, your talk was great. That's what I'll add.
Now, a couple other questions of you, young man, before I give you your big gift at the end of the evening. What do you plan to do? Where would you like to go? What area?
What area? Well, I would like to keep doing astrophysics. I would like to keep doing this. I mentioned in my bio that I would like to talk about gravitational lensing and gravitational waves, right? So like, again, just like light is a wave, I guess minus 5 masses. If you have like these gravitational waves, which are when two black holes are orbiting each other and emitting gravitational waves, so we see with fancy detectors like LIGO. If we have the same lenses, actually, it's the same effect, right? If the same lenses are going to bend that light, the wave, the gravitational wave, just like it bends light. And that effect should be observable in our current and upcoming detectors. So that would be very interesting if we could see signatures of that, right? Of course, the first thing to do is to detect it, and after that, once you know it's a reliable phenomenon, then you can start asking scientific questions like, well, can we use this to learn about dark matter again, right? Yeah, that would be really fun.
Okay, but I was thinking about university professor teaching. Alex Filippenko started that, and that's
I think
there.
that it would be nice to go do a postdoc at least. Yeah.
You haven't set your sights on JPL or NASA?
Yeah, I mean, that would be really nice.
Well,
Actually.
Yeah. And a typical day for you out there these days, are you on a telescope or just sitting around kicking this stuff around?
I mostly sit on my desk doing a lot of coding and math. That's my day-to-day.
Well, you did good, and we have to give away to our speakers the ancient Chumash tote bag that they dug up out here by the tree. This is an actual rendering of the cup they used to serve in one of the early Starbucks. Your check inside your honorarium, ladies and gentlemen. Joaquin Becerra. Close this down here in a minute. This is the first time everybody hasn't gotten up and left. But next month it's Dr. Rosalie Lopez of JPL talking about volcanism. I'm working on getting one of the daughters of legendary, I guess late, Professor Frank Drake to come talk to us, the Drake equation. I think he probably passed on. But I have a source. He mysteriously disappeared. Okay, so next month we hope to see you back here on the 6th.
Okay. See you next month.
There's a button that says for a membership. Can that be a PDF? It should be a PDF. I think it is. Take a look at that.